In the spring of 1961, the United States was losing the space race, and losing badly. The Soviet Union had just launched Yuri Gagarin into orbit, making him the first human being to leave Earth's atmosphere and return alive. Meanwhile, America's most advanced achievement was a 15-minute suborbital hop that barely grazed the edge of space. Alan Shepard had gone up and come down in less time than it takes to watch a sitcom. And yet, on May 25th of that same year, President John F. Kennedy stood before Congress and made a promise so audacious, so seemingly impossible, that even the people running NASA thought he might have lost his mind. "We choose to go to the moon," Kennedy declared. "Not because it's easy, but because it's hard. And we're going to do it before this decade is out." Let me put this in perspective. Kennedy had just committed the United States to accomplishing something that required technology that didn't exist, using materials that hadn't been invented, solving problems that nobody understood, and doing it all in less than 9 years. At that moment, NASA couldn't even keep a man in orbit for more than 90 minutes. They had never docked 2 spacecraft. They had never performed a spacewalk. They had never built a rocket powerful enough to escape Earth's gravity. They had never landed anything on another celestial body. They had never brought anything back from space intact. And now they were supposed to do all of that, plus invent a dozen other capabilities from scratch, and, oh, by the way, bring 3 men safely home from 250,000 miles away. It was like promising to climb Mount Everest when you've only ever walked up a hill in your backyard. But here's the thing about impossible challenges. Sometimes they force human beings to become something more than they thought possible. Sometimes they push engineering to places it's never been before. And sometimes, just sometimes, they work. This is the story of Apollo 11 and the insane engineering that made it possible. Let's start with the most obvious problem. Getting to the moon isn't like flying to another country. It's not even like flying to another planet. The moon sits 240,000 miles from Earth, which means you have to travel roughly 10 times the distance around the Earth's equator just to get there. And you have to do it through the vacuum of space, where there's no air, no oxygen, no atmospheric pressure, and temperatures that swing from 250 degrees Fahrenheit in the sunlight to minus 250 degrees in shadow. Oh, and you have to land on a surface that has no atmosphere to slow you down, which means you can't use parachutes. You have to use rockets to brake, and those rockets have to work perfectly because there's no second chance. Miss your landing site by a few miles, and you might crash into a crater or a boulder field. Run out of fuel before touchdown, and you're a meteor. And then, after you've somehow survived all of that, you have to take off again from a place with no launch pad, no ground support, no mission control, and if that single engine doesn't fire on the first try, you die on the moon. Oh, and one more thing. You have to do all of this with 1960s technology. No GPS, no satellite communications, no modern computers, no advanced materials, just slide rules, vacuum tubes, and an insane amount of human ingenuity. So, how do you even begin to solve a problem like this? You start with the rocket. And not just any rocket. You need the most powerful machine ever built by human beings. You need something so large, so powerful, so ambitious that it makes every other engineering project in history look like a science fair experiment. You need the Saturn V. The numbers alone are almost incomprehensible. 363 feet tall. That's a 36-story building. 6.5 million pounds at liftoff. That's the weight of about 400 elephants, or 50 blue whales, or one really ambitious ego. And it generates 7.6 million pounds of thrust at liftoff, which is enough force to lift the entire rocket off the ground and accelerate it to 17,000 miles per hour in less than 12 minutes. To put that in perspective, if you stood 3 miles away from a Saturn V launch, the sound would still be loud enough to cause physical pain. The shock waves from the engines were so powerful that they could be detected by seismographs hundreds of miles away. The flame trench beneath the launch pad had to be doused with millions of gallons of water, not to extinguish any fire, but to dampen the acoustic energy so the sound waves wouldn't tear the rocket apart before it even left the ground. This thing was so loud that it remains, to this day, the loudest human-made sound ever produced. But building something big and loud is one thing. Building something big and loud that actually works is something else entirely. The heart of the Saturn V was the F1 engine, and the F1 was a monster. Each engine stood 19 feet tall, weighed 18,000 pounds, and burned 3 tons of fuel every second. Every second. Let that sink in for a moment. 3 tons of fuel, gone, in the time it takes you to blink. The Saturn V had 5 of these engines clustered together on its first stage, which meant that at liftoff, the rocket was consuming 15 tons of fuel per second. That's 30,000 pounds of liquid oxygen and kerosene disappearing into fire and thrust every single second. The fuel tanks held 540,000 gallons of propellant, and the Saturn V drained them completely in just 2.5 minutes. But here's where things get interesting. The F1 engine was so powerful that it kept destroying itself during testing. Engineers at Rocketdyne, the company building the engines, kept running into a problem called combustion instability. Basically, when you're burning fuel that fast, in a chamber that hot, under that much pressure, the combustion process can become unstable. Instead of a smooth, controlled burn, you get oscillations. Pressure waves that bounce around inside the combustion chamber, amplifying with each bounce until the whole thing starts to resonate like a tuning fork. Except this tuning fork is filled with fuel burning at 6,000 degrees Fahrenheit, and when it resonates, it explodes. And explode it did, again and again. Test engines would fire up, run for a few seconds, and then detonate with enough force to leave craters in the test stand. Engineers tried everything. They changed the fuel mixture. They adjusted the injection patterns. They modified the chamber geometry. Nothing worked. The combustion instability was like trying to smooth out a wave in a bathtub. Every fix they tried just created new problems. Finally, in an act of desperation that bordered on madness, they tried something that sounds more like a Looney Tunes cartoon than serious engineering. They started bombing the engines. Literally. While the engines were running at full power, they would detonate small explosive charges inside the combustion chamber to see if the engine could survive the shock. The logic was simple. If the engine could handle a deliberate explosion and keep running smoothly, then it could probably handle combustion instability. And you know what? It worked. By systematically testing different injector designs and combustion chamber shapes, and bombing the hell out of them in the process, Rocketdyne eventually figured out an injector plate design that created a stable burn pattern. The F1 engine became reliable. Well, as reliable as something that consumes 3 tons of fuel per second and produces enough thrust to launch a skyscraper can be. But even with working engines, you still have to feed them. And feeding 5 F1 engines is a problem that would make most engineers weep. You need to pump 540,000 gallons of fuel into the combustion chambers in less than 3 minutes. That's not just a lot of fuel. That's a lot of fuel moving very fast through very large pipes under very high pressure. The fuel pumps on the Saturn V were themselves engineering marvels. The liquid oxygen pump spun at 5,600 revolutions per minute and could move 13,000 gallons of super-cold liquid oxygen per minute. The RP-1 kerosene pump wasn't far behind. These pumps were driven by turbines that were themselves powered by burning some of the rocket fuel in a separate chamber. It was a rocket engine that powered pumps that fed a bigger rocket engine. And all of this had to work perfectly, in sync, for 2.5 minutes straight, or the rocket would fail. And then there's the problem of keeping everything cold. Liquid oxygen boils at minus 297 degrees Fahrenheit. Liquid hydrogen, which was used in the upper stages, boils at minus 423 degrees. These aren't just cold. These are temperatures that turn regular metals brittle. These are temperatures where a wrench dropped on a fuel line could shatter it like glass. The fuel tanks had to be insulated, but not too much because, remember, every ounce matters. They had to be vented because the fuel was constantly boiling off, turning into gas, building up the pressure that could rupture the tanks if it wasn't released. They had to be topped off continuously right up until launch, because the fuel was literally evaporating faster than they could pump it in. Launch controllers had to time everything perfectly. Fuel the rocket too early and you'd lose too much to boil off. Fuel it too late and you'd miss your launch window. The margin for error was measured in minutes. But let's say you've solved all of that. You've got 5 engines that don't explode. You've got fuel pumps that work. You've got tanks that hold cryogenic fuel without shattering. Now, you have to make the whole thing fly. And that means computers. In 1961, computers were the size of rooms. They used vacuum tubes that generated so much heat you needed dedicated cooling systems just to keep them from melting. They were programmed using punch cards. They crashed constantly. And NASA needed to put one of these things in a spacecraft and trust it to navigate to the moon. The solution was the Apollo guidance computer, and it's one of the most important computers ever built. Not because it was powerful. It wasn't. Your phone has 4 million times more memory than the AGC. Not because it was fast. It wasn't. A modern calculator can outperform it, but because it worked. The AGC was the first computer to use integrated circuits. Microchips. Before Apollo, integrated circuits were an experimental technology. They were expensive. They were unreliable. Nobody was using them for anything important. But NASA placed an order for Apollo that required thousands of these chips, and that order basically created the entire microchip industry. Without Apollo, we might not have personal computers today. We might not have smartphones. We might not have the internet. The AGC was also the first computer to use a revolutionary concept called fly-by-wire. Before this, all spacecraft and aircraft controls were mechanical. You moved a stick, and that stick was physically connected to control surfaces or thrusters through cables and hydraulics. But the AGC interpreted commands from the astronauts and translated them into the precise thruster firings needed to maneuver the spacecraft. The astronauts weren't flying the spacecraft directly. They were telling the computer what they wanted to do, and the computer figured out how to do it. This was terrifying to pilots. These were test pilots, fighter jocks, men who were used to having direct physical control over their machines. And now they were being asked to trust their lives to a box of electronics that could fit under an airplane seat. A box that had less computing power than a modern car key fob, but it worked. The AGC guided Apollo spacecraft to the Moon and back with incredible precision. It handled navigation, guidance, and control. It managed the life support systems. It ran the landing radar and the rendezvous radar. It did all of this while running multiple programs simultaneously, a concept called multitasking that didn't exist in commercial computers for another 20 years. But even with a working computer, you still have the fundamental problem of rocket staging. The Saturn V was so large and carried so much fuel that it couldn't possibly reach orbit as a single unit. It had to shed weight as it climbed. The solution was to build it in 3 stages. The first stage, the S-1C, burned for 2.5 minutes and lifted the entire stack to about 40 miles altitude and 6,000 miles per hour. Then it separated and fell away. The second stage, the S-2, took over and burned for 6 minutes, pushing the spacecraft to orbital velocity. Then it separated. The third stage, the S-4B, did the final push into Earth orbit and later reignited to send the spacecraft toward the Moon. Simple in concept, nightmarish in execution. Stage separation sounds easy until you realize you're trying to pull apart a 363-foot rocket while it's traveling at 6,000 miles per hour. You can't just disconnect the stages and hope they drift apart. They're still moving together at the same speed. You need to actively push them apart, and you need to do it without damaging anything. The solution involved explosive bolts, retro rockets, and something called ullage motors. The explosive bolts were exactly what they sound like, bolts with small explosive charges built in. When separation was commanded, these charges would detonate, severing the connection between stages. But that only disconnected them. To actually separate the stages, retro rockets on the lower stage would fire, slowing it down so it would fall away. Meanwhile, ullage motors on the upper stage would fire, pushing it forward. Ullage motors served another purpose too. In the zero-gravity environment of space, the fuel in the tanks would float around randomly. Before you could ignite the next stage's engines, you needed the fuel settled at the bottom of the tanks, where the pumps could reach it. The ullage motors provided just enough acceleration to push the fuel to the back of the tanks. It was a tiny amount of thrust, just enough to create the feeling of gravity inside the fuel tanks, but it was crucial. And then there's the weight obsession. Every single component on the Saturn V was scrutinized for unnecessary weight. Engineers would file down bolt threads to save a few ounces. They would drill holes in brackets. They would use aluminum instead of steel wherever possible. They would make parts thinner and thinner, testing them to failure, then backing off just enough to ensure they'd survive. Why? Because of the tyranny of the rocket equation. The rocket equation is a mathematical relationship that describes how much fuel you need to achieve a certain velocity. And it's brutal. To go faster, you need more fuel. But more fuel means more weight. And more weight means you need even more fuel to lift that weight, which means more weight, which means more fuel. It's an exponential problem. Every pound of payload you want to send to the Moon requires roughly 100 pounds of fuel at liftoff. Want to add a 10-pound camera? That's a literal ton of extra fuel at launch. This is why the Apollo spacecraft had no seats. Seats were too heavy. The astronauts stood during launch, held in place by harnesses. This is why the Lunar Module, which we'll get to later, had walls so thin you could poke your finger through them. This is why engineers spent months figuring out how to remove every unnecessary gram from every component. Weight was the enemy. And in the obsessive war against weight, engineers became artists of efficiency, sculptors of necessity, creating machines that were simultaneously the most complex and the most refined objects humans had ever built. The Saturn V first stage was made of aluminum so thin that it would collapse under its own weight when empty. It could only maintain its shape when pressurized with fuel or supported by internal structures during construction. The wiring harnesses were designed with such precision that each wire was cut to the exact length needed, not an inch longer. The insulation was the thinnest possible material that could still do the job. By November of 1967, after 6 years of round-the-clock work by more than 400,000 people, the Saturn V was ready for its first test flight. Apollo 4 was an unmanned test, and there was genuine fear that the rocket might explode on the pad or shortly after liftoff. The vibrations from 5 F-1 engines firing at once had never been experienced before. Nobody knew if the rocket would shake itself apart. When Apollo 4 lifted off on November 9, 1967, it was the loudest, most powerful, most spectacular thing anyone had ever seen. Walter Cronkite, reporting from the CBS News booth 3 miles away, watched as the ceiling tiles in his booth started falling down from the vibrations. The windows were rattling so hard he thought they might shatter. And he was 3 miles away. The rocket rose slowly at first, almost leisurely, as if considering whether it really wanted to leave Earth. But then the engines reached full power, and the Saturn V began to accelerate. And it just kept accelerating, faster and faster, pushing itself and 11 astronauts' worth of hopes and dreams toward the heavens on a pillar of fire that could be seen for hundreds of miles. Apollo 4 was a complete success. Every stage fired perfectly. Every separation happened exactly as planned. The spacecraft reached orbit, then reignited the third stage to simulate the trans-lunar injection burn, then separated and performed a high-speed re-entry to test the heat shield. Everything worked. 2 more unmanned tests followed, Apollo 5 and 6, testing various components and configurations. And then, in December 1968, Apollo 8 became the first manned flight of the Saturn V, and it went straight to the Moon. No test flights in Earth orbit. No gradual approach. Frank Borman, Jim Lovell, and Bill Anders climbed aboard a rocket that had flown exactly twice before and rode it to lunar orbit. The audacity of that decision still boggles the mind, but that's how desperate NASA was to meet Kennedy's deadline. They couldn't afford to take it slow. They couldn't afford to be cautious. They had less than 2 years left to make good on the promise. The command module was the crown jewel of the Apollo spacecraft, and it was possibly the most sophisticated pressure vessel ever constructed. Picture a gumdrop shape, about 11 feet tall and 13 feet in diameter at its widest point. Now imagine that this gumdrop has to keep 3 men alive in the vacuum of space for up to 2 weeks, protect them from temperatures that swing wildly between extreme heat and extreme cold, bring them home through a re-entry that subjects them to forces that would flatten a normal aircraft, and do all of this with 1960s technology. The command module wasn't just a spacecraft. It was a self-contained world, a miniature Earth hurtling through the void, and every single system had to work perfectly or the crew would die. There was no rescue mission possible. No one could come get them if something went wrong. They were on their own, 250,000 miles from home, with only the engineering decisions made by thousands of people back on Earth standing between them and the infinite cold of space. Let's start with the most critical component, the one thing that absolutely had to work, or the astronauts would burn up like meteors. the heat shield. When the command module returned from the Moon, it would slam into Earth's atmosphere at 25,000 miles per hour. At that speed, the compression of air in front of the spacecraft creates temperatures that reach 5,000 degrees Fahrenheit. That's hot enough to melt steel, titanium, aluminum, and pretty much every conventional material known to man. The heat shield had to survive this, and it had to do so while protecting the astronauts inside. The solution was an ablative heat shield, and it represented some of the most sophisticated materials science of the era. The shield was made of a honeycomb structure filled with a phenolic epoxy resin. When this material heated up during re-entry, it would char and then ablate away, meaning it would literally vaporize and blow off in chunks. This sounds like a terrible thing, like your heat shield is disintegrating, but it's actually genius. As the material ablates, it carries away enormous amounts of heat. The process of turning solid material into gas requires massive amounts of energy, and that energy comes from the heat that would otherwise be cooking the astronauts. The ablating material also creates a boundary layer of gas between the spacecraft and the superheated plasma surrounding it, providing an extra layer of insulation. But here's the terrifying part. You can't really test an ablative heat shield under real conditions. You can do lab tests. You can subject samples to high temperatures in furnaces. You can run simulations. But you can't actually test the whole shield under the exact conditions of lunar return re-entry until you do it for real. The heat shield on Apollo 11 had never been proven to work at lunar return velocities. The previous Apollo missions, including Apollo 10, which went to the Moon, had tested various aspects of the heat shield, but each mission was essentially a test. Each crew was betting their lives that the engineers had gotten the math right, that the materials would perform as predicted, that nothing unexpected would happen during those 4 minutes of searing heat and communications blackout when the spacecraft was wrapped in a cocoon of plasma so hot and dense that radio waves couldn't penetrate it. The heat shield was just the beginning. Inside the command module, the astronauts needed to breathe, and that meant creating and maintaining an artificial atmosphere. On Earth, we take air for granted. It's just there. 21% oxygen, 78% nitrogen, about 1% other stuff, at a pressure of 14.7 pounds per square inch. Simple. But in space, nothing is simple. The first decision NASA made was to use pure oxygen instead of an Earth-like mixture of oxygen and nitrogen. Why? Weight. Nitrogen is an inert gas. It doesn't do anything useful for respiration. It's just there as a buffer. If you fill a spacecraft with an Earth-normal mixture of oxygen and nitrogen at Earth-normal pressure, you need heavy tanks to hold all that gas, and you need a strong, heavy pressure vessel to contain it. But if you use pure oxygen at a lower pressure, say 5 pounds per square inch instead of 14.7, you can make the spacecraft walls thinner and lighter, and you need less gas volume. The astronauts would still get the same amount of oxygen they need, because even though the pressure is lower, the oxygen concentration is higher. It seemed like a brilliant solution, until Apollo 1. On January 27, 1967, astronauts Gus Grissom, Ed White, and Roger Chaffee were conducting a routine test inside the Apollo 1 command module. The cabin was pressurized with pure oxygen at 16.7 pounds per square inch, which was higher than the planned flight pressure, but standard for ground tests because it helped detect leaks. During the test, a spark from damaged wiring ignited some nylon netting. In normal air, the fire would have been bad but manageable. In pure oxygen at high pressure, it was apocalyptic. The fire spread faster than anyone thought possible. Materials that were considered non-flammable in normal air burned furiously in the oxygen-rich environment. Velcro burned. The astronauts' spacesuits burned. Aluminum burned. The temperature inside the cabin rose so fast that the pressure vessel ruptured. All 3 astronauts died within seconds, likely from smoke inhalation before the flames reached them. It was a horrific tragedy, and it forced NASA to completely rethink the atmosphere system. After Apollo 1, NASA redesigned everything. They removed flammable materials from the cabin. They replaced nylon with beta cloth, a fireproof material made from fiberglass. They redesigned the hatch so it could be opened in seconds instead of minutes, and they changed the atmosphere protocol. For ground tests and during launch, the cabin would be filled with a mixture of 60% oxygen and 40% nitrogen at normal pressure. Once in space, the cabin would be slowly vented, allowing the nitrogen to escape, until it reached pure oxygen at 5 pounds per square inch. This compromise gave them the safety of a non-pure oxygen environment during the most dangerous phases of flight, while still allowing them the weight savings of pure oxygen in space. But maintaining this atmosphere required constant vigilance. The astronauts were breathing, which consumed oxygen and produced carbon dioxide. The electronics were running, generating heat and sometimes outgassing materials. The cabin had to maintain the right pressure, the right temperature, the right oxygen level, and somehow scrub the carbon dioxide before it built up to toxic levels. The CO2 scrubbers were canisters filled with lithium hydroxide, a chemical that absorbs carbon dioxide. As air circulated through the cabin, fans pushed it through these canisters, and the lithium hydroxide would react with the CO2, removing it from the air. Simple chemistry, but absolutely critical. If the scrubbers failed, or if they became saturated and couldn't absorb any more CO2, the astronauts would slowly suffocate on their own exhalations. The command module carried enough lithium hydroxide canisters for the planned mission duration, plus several days of margin. But, as Apollo 13 would later prove, sometimes margin isn't enough. When the Apollo 13 service module exploded, the crew had to shut down the command module to save power and retreat to the Lunar Module, which was only designed to support 2 men for 2 days. Now it had to support 3 men for 4 days. The Lunar Module had its own CO2 scrubbers, but they were a different shape and size than the command module scrubbers. The Lunar Module's supply of canisters ran out, but the command module had plenty. The problem was they didn't fit. The command module canisters were square. The Lunar Module receptacles were round. In one of the most famous scenes in spaceflight history, engineers on the ground had to figure out how to adapt square canisters to round holes using only materials available on the spacecraft: plastic bags, cardboard, tape, and hoses from the spacesuits. They literally built an adapter out of trash, radioed the instructions to the astronauts, and it worked. The crew of Apollo 13 survived because someone figured out how to make a square peg fit in a round hole. But let's get back to Apollo 11, where everything was working as planned. The command module didn't just need to maintain atmosphere, it needed to navigate. And navigating in space is nothing like navigating on Earth. On Earth, you have landmarks. You have the sun rising in the east and setting in the west. You have the North Star. You have GPS if you're living in the modern era. In space, you have none of that. Well, you have stars, but they don't rise or set because there's no horizon. They just sit there, fixed in their positions unless you're moving, in which case they appear to move, but in ways that aren't intuitive. The Apollo guidance system used a combination of the Apollo guidance computer, an inertial measurement unit, a sextant, and a telescope. The inertial measurement unit, or IMU, was essentially a set of gyroscopes that could measure the spacecraft's orientation and any changes in its velocity. Gyroscopes are devices that spin very fast and resist any attempt to change their orientation. By mounting 3 gyroscopes at right angles to each other, you can measure rotation in all 3 axes. The IMU could tell the astronauts which way the spacecraft was pointing and how fast it was moving. But gyroscopes drift over time. Small errors accumulate. If you rely solely on the IMU, you'll eventually get lost. So, the Apollo system also included a sextant and a telescope that the astronauts could use to take sightings of stars and landmarks. The sextant worked just like the sextants used by ships at sea for centuries, except instead of measuring the angle between a star and the horizon, it measured the angle between 2 stars, or between a star and the moon or Earth. The astronauts would sight a known star, then sight a landmark on the moon or Earth, and the angle between them would tell the computer exactly where the spacecraft was and which direction it was pointing. The computer would compare this measurement to what the IMU thought the position and orientation were, calculate the error, and correct the drift in the gyroscopes. This process was called realignment, and the astronauts did it regularly throughout the mission. The Apollo guidance computer was remarkable, not just for what it could do, but for how it did it. The AGC had 74 kilobytes of memory. Let me repeat that. 74 kilobytes. A single image from your phone's camera is larger than the entire memory capacity of the computer that guided humans to the moon. But what made the AGC special wasn't the amount of memory. It was how that memory was designed. The main memory was something called core rope memory, and it was literally woven by hand. Tiny magnetic cores, about the size of a pinhead, were arranged in a grid. Wires were threaded through these cores in specific patterns. If a wire went through a core, that represented a binary 1. If it went around the core, that represented a binary 0. The software was literally woven into the hardware by women working with needles and microscopes, threading wires through cores in patterns that represented the program code. It was painstaking work. A single mistake, one wire threaded through the wrong core, could crash the entire system. And once the rope memory was woven, it was permanent. You couldn't reprogram it. You couldn't patch it. If engineers found a bug in the software, they couldn't just upload a fix. They had to weave an entirely new rope memory module, which took weeks. This meant that the software had to be perfect before launch. Testing was exhaustive. Thousands of hours of simulations, trying to break the software, trying to find edge cases and failure modes. The AGC software was written by a team at MIT, led by a woman named Margaret Hamilton, and it included revolutionary concepts that wouldn't appear in commercial software for decades. One of these concepts was priority scheduling. The AGC had to run multiple programs at the same time. It had to handle navigation calculations, control the thrusters, manage the displays, and respond to input from the astronauts. But the computer could only execute one instruction at a time. So, how do you run multiple programs simultaneously? You give each program a priority level, and you let the computer rapidly switch between programs, executing a few instructions from each one in turn. High-priority programs, like those controlling the thrusters, would get more processor time. low-priority programs like updating the display would get less. If the computer got overloaded, it would shed the lowest priority tasks first, ensuring that the critical systems kept running. This priority scheduling system would save Apollo 11 during the moon landing, but we'll get to that later. The AGC interface was a display and keyboard unit called the DSKY, pronounced DISKY. It had a simple numeric display and a keyboard with 19 keys. The astronauts communicated with the computer using verb-noun pairs. A verb was an action, like display or load or perform. A noun was a piece of data, like velocity or altitude or program. To ask the computer for the current velocity, you'd enter verb 16, which meant display, and noun 36, which meant velocity. The computer would then show the velocity on the display. To tell the computer to run a specific program, you'd enter verb 37 and the program number. It was an elegant system that allowed for complex interactions using just a simple numeric keypad. But it required the astronauts to memorize dozens of verb and noun codes and to understand what each combination would do. Training on the AGC was intensive. Astronauts spent hundreds of hours in simulators, practicing normal operations and emergency procedures until they could operate the DSKY in their sleep. Now, the command module couldn't reach the moon on its own. It needed a service module, a cylindrical section attached to the base of the command module that held the main engine, fuel tanks, oxygen tanks, fuel cells, and other systems. Together, the command and service modules formed the CSM. The Service Propulsion System Engine, or SPS, was the only engine capable of taking the spacecraft out of lunar orbit and sending it back to Earth. If the SPS failed while in lunar orbit, the astronauts would be stranded. There was no backup, no rescue mission. They would orbit the moon until their oxygen ran out. The pressure on the engineers who designed the SPS was immense. It had to be reliable. It had to work on the first try, every time. The SPS used hypergolic propellants, meaning fuels that ignite on contact with each other. The fuel was a mixture called Aerozyne 50, which was 50% hydrazine and 50% unsymmetrical dimethylhydrazine. The oxidizer was nitrogen tetroxide. When these two chemicals mix, they ignite spontaneously. You don't need a spark. You don't need an ignition system. You just need to let them touch, and boom, you have thrust. This made the SPS incredibly reliable because there were fewer things that could go wrong. No spark plugs to fail. No ignition coils to malfunction. Just valves that opened and let the fuel and oxidizer flow into the combustion chamber. The downside of hypergolic propellants is that they're incredibly toxic. Nitrogen tetroxide is corrosive and poisonous. Hydrazine is even worse. A single drop on your skin can be fatal. The fuels had to be handled with extreme care during loading, and any leaks in space could be catastrophic. But the reliability was worth the risk. The command module also had a system of thrusters for maneuvering. These were smaller rockets arranged around the exterior of the service module, and they allowed the spacecraft to rotate, translate, and make small adjustments to its trajectory. The thrusters used the same hypergolic propellants as the SPS. There were 16 thrusters in total, arranged in 4 groups of 4. If some of the thrusters failed, the others could compensate. This redundancy was critical because the spacecraft needed attitude control at all times. In space, there's no air, so you can't use aerodynamic control surfaces like rudders or ailerons. You can only change your orientation by firing thrusters. Lose attitude control and you're tumbling helplessly. You can't align your heat shield for re-entry. You can't point your antenna at Earth. You can't dock with the Lunar Module. You're done. So the thruster system was designed with multiple levels of redundancy. Fuel lines could be isolated. Different tanks could be selected. Even if several thrusters failed, the astronauts could still control the spacecraft. Then there's the windows. The command module had 5 windows, 2 side windows, 2 forward-facing rendezvous windows, and a central hatch window. These weren't just any windows. They had to be optically perfect because the astronauts used them to take star sightings for navigation. Any distortion could throw off the measurements. They had to withstand the pressure differential between the cabin and the vacuum of space. They had to handle the thermal extremes of direct sunlight and deep shadow. And they had to not shatter during launch or re-entry. Each window was made of 3 panes of glass, silica on the inside, then a stronger tempered glass in the middle, then a layer of fused silica on the outside. The layers were designed to handle different stresses. The inner pane held the cabin pressure. The middle pane provided structural strength. The outer pane protected against temperature extremes and micrometeorite impacts. The windows were positioned to give the crew maximum visibility during critical operations. The rendezvous windows were angled so the astronauts could see the lunar module during docking maneuvers. The side windows allowed them to see the moon during orbit. The positioning of these windows was the result of countless hours of analysis and simulation, figuring out exactly where the crew would need to look during each phase of the mission. Communication was another critical system. The command module had multiple radio systems operating on different frequencies. The S-band system was the primary long-range communication link with Earth. It could transmit voice, telemetry data, and even slow-scan television images. The VHF system was used for short-range communications with the Lunar Module. During the moon landing, when the LM was on the surface and the command module was orbiting overhead, they'd communicate using VHF. The antennas had to be positioned carefully. In space, you can't just stick an antenna on top of the spacecraft and assume it will work in all directions. The spacecraft is constantly rotating, and parts of the structure can block the signal. The CSM had multiple antennas, and the computer would automatically select the one with the best line of sight to Earth. If the automatic system failed, the astronauts could manually select antennas and even rotate the spacecraft to improve the signal. During re-entry, all communication was lost for about 4 minutes. The plasma surrounding the spacecraft was so dense that radio waves couldn't penetrate it. This was one of the most tense periods of any Apollo mission. Ground control would watch the clock, knowing that the spacecraft should emerge from the blackout at a specific time. If that time came and went with no signal, something had gone wrong. The heat shield had failed, or the trajectory was off, or the parachutes didn't deploy. There was nothing anyone could do but wait and hope. And speaking of parachutes, the landing system was yet another marvel of engineering that had to work perfectly on the first try. The command module returned from space at 25,000 miles per hour. The heat shield slowed it down to about 300 miles per hour by the time it reached lower altitude. But that's still way too fast to survive impact with the ocean. The command module weighed 12,000 pounds. Hitting the water at 300 miles per hour would be like hitting concrete. The astronauts would be killed instantly. So the spacecraft needed parachutes, and not just any parachutes. It needed a complex sequence of parachutes that would deploy at specific times and altitudes. First, at about 24,000 feet, the forward heat shield would jettison. This was a smaller heat shield covering the nose of the command module where the parachutes were stored. Explosive bolts would fire, and small rockets would push the forward heat shield away. Then, 2 drogue parachutes would deploy. These were small, 16-foot diameter parachutes designed to stabilize the spacecraft and slow it from 300 miles per hour to about 175. The drogues weren't strong enough to land the spacecraft. They were just there to slow it down enough that the main parachutes could deploy without being torn apart. At 10,000 feet, the drogue chutes would be released, and the 3 main parachutes would deploy. These were massive, 83-foot diameter parachutes, each one large enough to cover a basketball court. They deployed in stages. First, they'd come out as small pilot chutes, which would pull out the main canopy. The canopy would inflate gradually, avoiding a sudden shock that could tear the fabric. Once fully deployed, the 3 main chutes would slow the command module to about 22 miles per hour for splashdown. But even this system had redundancy. The spacecraft could land safely on just 2 of the 3 main parachutes. The designers knew that parachutes could fail. A line could break. A canopy could tear. So they built in the ability to lose 1 chute and still survive. During Apollo 15, one of the 3 main parachutes did fail, collapsing during descent. The other 2 held, and the crew landed safely, though the impact was harder than normal. The parachute system was tested exhaustively. Engineers dropped test articles from aircraft at high altitude, simulating different failure modes. They tested the parachutes in wind tunnels. They tested the deployment mechanisms. They tested the explosive bolts that released the forward heat shield. Every component was tested to destruction to find its limits, then a safety margin was added. And even with all that testing, every Apollo crew knew that they were betting their lives on a parachute system that had never been used in actual lunar return conditions until they did it for real. Inside the command module, the crew had to survive for up to 2 weeks in a space not much larger than a walk-in closet. The interior was packed with equipment. Control panels covered nearly every surface. Switches, dials, circuit breakers, displays. There were over 600 switches and controls that the astronauts needed to know how to operate. The crew couches were custom molded to each astronaut's body, providing support during launch and re-entry when they'd experience forces up to 6 times Earth's gravity. But in space, the couches were uncomfortable and took up valuable room, so the astronauts spent most of the mission floating around the cabin. They slept in sleeping bags that could be attached to the couches or to the walls. Food was stored in plastic packages and eaten with spoons. Water came from the fuel cells that generated electricity by combining hydrogen and oxygen. This water was a byproduct of power generation, and it was actually quite pure, though the astronauts reported that it tasted strange and sometimes caused gas because of residual hydrogen. Waste management was primitive. There were no toilets. The astronauts used bags for solid waste and a hose for liquid waste. It was uncomfortable, undignified, and one of the least discussed challenges of spaceflight. For short missions like Apollo 11's 8-day duration, it was tolerable, if barely. The command module represented the absolute cutting edge of human engineering. A machine that had to be simultaneously strong enough to survive launch and re-entry, yet light enough to be launched, sophisticated enough to navigate across 250,000 miles of space, yet simple enough to be operated by 3 men with no ground support when communications were lost. It was a pressure vessel, a spacecraft, a navigation platform, and a home. And in July of 1969, it worked perfectly. July 20th, 1969. 4 days into the mission, and everything has gone almost perfectly. Apollo 11 launched from Kennedy Space Center on July 16th aboard a Saturn V that performed flawlessly. The trans-lunar injection burn sent the Command and Service Module, call sign Columbia, and the Lunar Module, call sign Eagle, on a 3-day coast toward the Moon. Neil Armstrong, Buzz Aldrin, and Michael Collins have checked and rechecked their systems. They've made small course corrections. They've eaten, slept as well as anyone can sleep in zero gravity, and watched the Earth shrink behind them while the Moon grew larger ahead. On July 19th, they fired the Service Propulsion System engine to slow down and enter lunar orbit, a maneuver that had to work perfectly or they'd shoot past the Moon and be lost in space. It worked. They've now completed several orbits, photographing the landing site, preparing for the most dangerous part of the mission: the descent to the surface. Armstrong and Aldrin have crawled through the docking tunnel into the Lunar Module, sealed the hatches behind them, and are running through their checklists. Michael Collins, alone in the command module, will remain in orbit, waiting for his crewmates to return. If something goes wrong, if the lunar module crashes or the ascent engine fails to ignite, Collins will have to return to Earth alone, leaving Armstrong and Aldrin on the Moon. It's a scenario that everyone has thought about, but nobody talks about. Collins has even practiced the procedures for solo operations: how to manage the command module by himself, how to set up the communication systems, how to perform the re-entry burns. He knows that if his crewmates don't come back, he'll be returning to Earth as the man who went to the Moon but didn't land, the man who came home when his friends didn't. It's a burden no one should have to carry, but someone has to stay in orbit. Someone has to bring Columbia home. At approximately 102 hours into the mission, the lunar module separates from the command module. Small springs push the two spacecraft apart. Eagle begins a slow tumble as it drifts away, and Collins in Columbia fires his thrusters to increase the separation. The two spacecraft are now independent, each with its own trajectory, its own life support, its own destiny. Armstrong and Aldrin are standing in the LM, held in place by cables and Velcro, looking out the triangular windows at the gray cratered surface of the Moon passing 60 miles below. They're running through checklists, checking systems, preparing for the most critical burn of their lives: the descent orbit insertion burn. This is a small burn, just 30 seconds, using the descent engine at 10% thrust. Its purpose is to change their orbit from a circular 60-mile altitude to an elliptical orbit that brings them within 50,000 feet of the surface at its lowest point. This elliptical orbit will be their starting point for powered descent. The burn has to be precise. Too much thrust and they'll come in too low, possibly impacting the surface. Too little thrust and they'll stay too high and won't be able to land. But the burn goes perfectly. Eagle drops into its descent orbit, and Armstrong reports back to Houston. Everything is looking good. Systems are nominal. They're go for powered descent initiation. At approximately 102 hours and 33 minutes into the mission, Eagle reaches the lowest point of its elliptical orbit, and the moment arrives. Powered descent initiation, PDI. The descent engine ignites, and suddenly Armstrong and Aldrin are no longer in free fall. They feel weight again for the first time in 4 days as the engine pushes against them, decelerating the spacecraft. The engine starts at 10% thrust, then ramps up to full power, 10,000 pounds of thrust, slowing Eagle from 3,800 miles per hour in orbit to 0 at the touchdown. This will take 12 minutes. 12 minutes of continuous engine burn, with the computer controlling the throttle and the spacecraft's attitude, guiding them toward a predetermined landing site in the Sea of Tranquility. Armstrong and Aldrin are monitoring the displays, watching the altitude and velocity counters tick down, ready to take over manually if something goes wrong. The first few minutes of the descent are what's called the braking phase. The spacecraft is still traveling forward at high speed, and the engine is firing almost straight backward, fighting to slow them down. They're also descending, but the primary goal right now is to kill their horizontal velocity. The spacecraft is pitched over at an angle, windows facing forward and down, giving the astronauts a view of the terrain they're approaching. The computer is flying the spacecraft, and the astronauts are calling out information to each other and to Houston. Altitude, velocity, fuel remaining. Houston is monitoring telemetry, watching the same numbers on their screens, ready to call an abort if anything looks wrong. Then, at about 6 minutes into the descent, when Eagle is at about 35,000 feet altitude and still descending, something happens. A light illuminates on the control panel, and a tone sounds in the astronauts' headsets. Program alarm. The display shows 12:02. Armstrong and Aldrin have trained for hundreds of potential problems, but 12:02 is not one they've seen before. It's not in their checklist. The computer is telling them something is wrong, but they don't know what. Armstrong calls down to Houston. Program alarm 12:02. What is it? In mission control, controllers are scrambling. 12:02. What's a 12:02? They're flipping through their documentation, trying to figure it out. The guidance officer, Steve Bales, is talking to his backroom support team. Jack Garman, a young computer engineer, recognizes the code. It's an executive overflow. The computer is receiving more data than it can process. It's overloaded. But is it critical? Can they continue? Garman knows that the computer has priority scheduling. If it's overloaded, it will shed low-priority tasks and keep the critical ones running. As long as the alarm isn't continuous, as long as the computer is still controlling the descent, they should be okay. Bales makes the call. He tells the flight director, Gene Kranz, that they're go. Kranz relays the decision to the spacecraft communicator, Charlie Duke, who transmits up to Eagle. "We're go on that alarm," Armstrong acknowledges. "Roger, go on that alarm." But his heart rate has jumped. The telemetry shows it. He was at 77 beats per minute. Now he's at 90. The alarm has rattled him, even though he won't admit it. The descent continues. Another minute passes and the alarm sounds again. 12:02. Armstrong calls it down. Houston responds. "We're go. Same alarm. They've analyzed it. The computer is handling it. Continue. But now a different alarm. 12:01. What's 12:01? Back in mission control, controllers are checking. 12:01 is another executive overflow. Slightly different from 12:02, but the same basic problem. The computer is overloaded. Bales and Garman confer again. They're still go. The computer is still flying the spacecraft. The alarms keep coming, but they're not continuous. The computer is clearing the errors and restarting critical tasks. It's working as designed. But Armstrong and Aldrin don't know this. They're seeing alarms, hearing tones, and they have to trust that Houston has analyzed the problem and made the right call. This is the nightmare scenario for any pilot. Warnings going off, systems misbehaving, and you're flying a spacecraft you've never flown before in an environment where a single mistake means death. and you have to trust the people on the ground to tell you whether to abort or continue. But they trust Houston, and they continue. Years later, it would be determined that the 1202 alarms were caused by a checklist error. The rendezvous radar, which wouldn't be needed until ascent, was left in the wrong mode. It was sending data to the computer continuously, even though the computer didn't need that data during descent. The extra data overloaded the computer, causing the alarms. The computer handled it beautifully, exactly as Margaret Hamilton and her team had designed it to do. It shed the unnecessary tasks, kept the critical navigation and control programs running, and guided the spacecraft toward the surface. The priority scheduling system that Hamilton had insisted on, over objections from some engineers who thought it was unnecessary, saved the mission. Without it, the computer would have crashed, and Armstrong and Aldrin would have had to abort. They would have returned to orbit without landing. Apollo 11 would have been a failure. But the system worked, and the descent continued. At about 8 minutes into the descent, Eagle transitions from the braking phase to the approach phase. The computer pitches the spacecraft more upright, giving the astronauts a better view of the landing site ahead. They're now at about 7,000 feet altitude, descending at about 100 feet per second, still moving forward toward the target. Armstrong is looking out the window, comparing what he sees to the maps and photos he studied during training. He's supposed to be heading for a relatively smooth area in the Sea of Tranquility, a plain free of large craters and boulders. But as the landing site comes into view, he realizes something is wrong. He sees a crater, a big one, and it's surrounded by a boulder field. Rocks the size of cars scattered everywhere. The computer is guiding them straight toward it. If they land there, they'll almost certainly crash. The boulders could tip the LM over or damage the landing gear. Armstrong knows he has to take over. He reaches for the attitude controller, small joystick-like device on his right side, and switches the computer from automatic to semi-automatic mode. In this mode, the computer will still control the throttle and keep the spacecraft stable, but Armstrong can adjust their horizontal position. He's going to fly over the boulder field and find a better spot. He pushes the controller forward, and Eagle begins to move farther downrange, flying over the terrain like a helicopter, looking for a place to land. But flying the LM manually is incredibly difficult. Armstrong is standing up, looking out a window angled downward, trying to judge altitude and distance to the surface, while also monitoring the displays showing velocity, fuel remaining, and altitude. The LM doesn't handle like any aircraft he's ever flown. There's no air, so there's no aerodynamic feedback. Every input he makes with the controller gets translated by the computer into thruster firings. Little puffs from the 16 attitude thrusters around the spacecraft. The spacecraft responds sluggishly because it's heavy and the thrusters are small. He has to lead his inputs, anticipating how the spacecraft will respond, and he's running out of fuel. The fuel gauge shows they have about 5% remaining. In a few minutes, they'll reach what's called bingo fuel, the minimum amount needed to abort safely and return to orbit. If they reach bingo and haven't landed, they have to abort. No exceptions. The mission rules are clear. Armstrong is flying as fast as he dares, skimming over the surface at about 30 feet per second horizontally while descending slowly, looking for a smooth spot. Aldrin is calling out altitude and fuel. 300 feet. 2% fuel, 200 feet. Aldrin can see the fuel gauge dropping. He knows they're running out of time. In Houston, controllers are watching the telemetry, seeing the fuel numbers drop, and they're getting nervous. Gene Kranz is ready to call an abort. The guidance officer is watching his display. 60 seconds of fuel remaining. He calls it out. 60 seconds. Charlie Duke relays it to the crew. 60 seconds. Armstrong acknowledges but doesn't look up. He's focused on the surface. He thinks he sees a clear area ahead, but he's not sure. He keeps flying. Aldrin continues calling out numbers. 100 feet, 75 feet. The descent is slowing now. Armstrong has found his spot and is bringing the LM down almost vertically. 50 feet. 30 seconds of fuel remaining. The call goes up from Houston. 30 seconds. Still, Armstrong doesn't respond. He's in the zone, every bit of his test pilot training and experience focused on this one task. 20 feet. The surface is close now. Dust is starting to blow outward from the descent engine exhaust. In the moon's vacuum, there's no air to slow the dust down, so it shoots out horizontally like a fluid, obscuring the surface. Armstrong is flying partially blind now, using his peripheral vision to judge altitude, watching for the contact light that will tell him the probes under the landing pads have touched the surface. 15 feet, 10 feet, still descending. Fuel is almost gone. In mission control, controllers are holding their breath. On the voice loop, someone whispers, "Come on, baby." Then a light on the panel. Contact light. One of the probes has touched the surface. Armstrong's hand moves instantly to the engine stop button. He presses it. The descent engine shuts down, and Eagle drops the last few feet under lunar gravity. The landing gear compresses, the honeycomb shock absorbers crushing slightly, and the spacecraft settles onto the surface with a gentle thump. For a moment, nobody says anything. Then Aldrin speaks. "Okay, engine stop." Armstrong is scanning the instruments, checking to make sure the spacecraft is stable, that they haven't landed on a slope too steep, that nothing is damaged. Everything looks good. He presses the transmit button. "Houston, Tranquility Base here. The Eagle has landed." In mission control, there's a brief pause as everyone processes what they just heard. Tranquility Base. Armstrong has changed the call sign. They're no longer Eagle. They're Tranquility Base. They've landed. Charlie Duke responds, and his relief is obvious in his voice. "Roger. Tranquility. We copy you on the ground. You got a bunch of guys about to turn blue. We're breathing again. Thanks a lot." The room erupts in cheers and applause. Grown men, engineers, and flight controllers who have spent years working toward this moment are crying, hugging each other, lighting cigars. Gene Kranz is trying to restore order, telling everyone to settle down. They still have work to do, but even he can't keep the smile off his face. In the spacecraft, Armstrong and Aldrin are going through the stay-no-stay checklist. They have to verify that all systems are functioning, that there are no leaks, that the spacecraft is stable and capable of launching again. If anything is wrong, they have to identify it immediately so they can either fix it or abort and launch back to orbit before they run out of consumables. They go through the checklist methodically, calling out each item. Fuel pressure. Good. Electrical systems. Good. Life support. Good. Communications. Good. Everything is nominal. They're staying. Houston gives them the formal go for stay. You are stay for T1, meaning they're cleared to remain on the surface for at least the next period before the next abort decision point. Armstrong and Aldrin acknowledge. They're on the moon, and they're not going anywhere for a while. The next several hours are a blur of activity. There's a timeline to follow, tasks to complete, but everyone is running on adrenaline. Armstrong and Aldrin are supposed to take a rest period. sleep for a few hours before the moonwalk, but nobody seriously expects them to sleep. They're standing in a spacecraft on the surface of the moon. Sleep is the last thing on their minds. After some discussion with Houston, the timeline is adjusted. They'll skip the rest period and go straight to preparing for the extravehicular activity, EVA, the moonwalk. But first, they have to depressurize the cabin, and that's not as simple as just opening a valve. The Lunar Module is pressurized to 5 pounds per square inch. Outside is vacuum. If they just opened the hatch, the air would explode outward, possibly damaging equipment or injuring the astronauts. They have to depressurize slowly, using a valve to vent the oxygen into space gradually. It takes several minutes. As the pressure drops, their suits automatically inflate to maintain the 5 pounds per square inch they need. Once the cabin pressure reaches 0, they can open the hatch. Armstrong is the first to go. He has to open the hatch, which opens inward, squeeze through the opening, then back out onto a small porch at the top of the ladder. It's an awkward maneuver in the bulky spacesuit, and it takes several minutes. Aldrin is helping, guiding Armstrong's backpack through the hatch, making sure nothing snags. Finally, Armstrong is outside, standing on the porch. He reaches for the ladder and begins descending. There are 9 rungs. The ladder is attached to one of the LM's landing legs. As Armstrong descends, Aldrin is watching from the window, and a TV camera mounted on the side of the descent stage is transmitting grainy black and white images back to Earth. 600 million people are watching on television, the largest audience in history. Armstrong reaches the bottom of the ladder. There's still a step down to the footpad, and then another step down to the surface. He's narrating everything as he goes, describing what he sees, what he's doing. The surface looks very fine-grained, he says, almost like a powder. He steps off the footpad onto the lunar surface, and as his boot sinks slightly into the dust, he speaks the words that will be repeated for generations. That's one small step for man, one giant leap for mankind. There's a slight audio glitch. The A before man is missing or inaudible, which changes the meaning slightly, but nobody cares. The moment is electric. A human being is standing on the moon. Armstrong is moving carefully, testing the footing, getting used to the 1/6 gravity. He reports that it's easier to move than expected. The surface is firm beneath the thin layer of dust. He's not sinking. He can walk without difficulty. 20 minutes later, Aldrin joins him, and the 2 astronauts begin their work. They have a long list of tasks. They have to deploy the flag, collect rock samples, set up scientific experiments, and document everything with photographs. The flag is a challenge. The flagpole won't go into the surface more than a few inches because there's a hard layer of regolith beneath the dust. They manage to get it standing, but it's leaning slightly, and they worry it might fall over. It doesn't. They plant the flag, and it becomes one of the most iconic images of the 20th century. 2 astronauts in white spacesuits standing next to an American flag on the barren, gray surface of the moon. The rock collection is scientifically the most important task. Armstrong and Aldrin are not geologists. They're pilots. But they've been trained to recognize interesting rocks and to collect a variety of samples. They're using tools specially designed for use in spacesuits with thick gloves. Tongs to pick up rocks. Bags to store them. A scoop to gather soil. Everything is more difficult in the suits. Simple tasks that would take seconds on Earth take minutes on the moon. Bending over is hard because the suit resists. The gloves make it difficult to grasp small objects. The dust sticks to everything, coating the suits, the tools, the sample bags. But they work efficiently, collecting samples as they move around the landing site. They're supposed to stay within 100 feet or so of the LM, and they're very aware of the timeline. They only have about 2.5 hours for the entire EVA. Time is running out. They deploy several scientific experiments: a passive seismometer to detect moonquakes, a laser retroreflector that scientists on Earth can bounce laser beams off to precisely measure the distance to the moon. These experiments will continue to operate long after the astronauts leave, sending data back to Earth for years. Armstrong makes a short trip to a nearby crater to take photographs and collect samples. This is the farthest he gets from the LM, about 200 feet. He wants to go farther, to explore more, but there's no time. The flight plan is strict. Finally, Houston calls up that it's time to wrap up. Armstrong and Aldrin gather the sample bags, the film magazines from the cameras, and prepare to climb back into the LM. Getting back up the ladder is harder than going down because they're carrying equipment and they're tired. The moonwalk has been physically demanding, even in 1/6 gravity. But they make it back inside, close the hatch, and begin repressurizing the cabin. They've been on the surface for 21 hours and 36 minutes. The EVA lasted 2 hours and 31 minutes. They're exhausted, but exhilarated. They've just done something no human has ever done before. They've walked on another world, but they're not done yet. They still have to launch off the moon, rendezvous with Columbia, and make the 3-day trip back to Earth. The hardest part, in some ways, is still ahead. But for now, they allow themselves a moment to rest, to eat, to look out the windows at the alien landscape surrounding them. Armstrong later describes the moon as beautiful in its own way. Stark, barren, lifeless, but beautiful. A place of magnificent desolation, as Aldrin called it. They try to sleep, but can't. The LM is cold and uncomfortable. There's no place to lie down, so they rig hammocks using cables and harnesses, but it doesn't help much. They doze fitfully for a few hours, then give up and start preparing for launch. The time has come. They've been on the moon long enough. It's time to go home. The Apollo program didn't just land humans on the moon. It fundamentally changed how we approach engineering problems of enormous scale and complexity. When Kennedy made his promise in 1961, NASA didn't have the answers. They didn't know how to build a rocket powerful enough. They didn't know how to navigate across 250,000 miles of space. They didn't know how to land on the moon or take off again. They didn't even know if it was possible. What they had was a deadline, a massive budget, and the collective determination of more than 400,000 people working toward a single goal. The solutions they developed, the engineering principles they established, the lessons they learned, those are perhaps more valuable than the moon rocks they brought back. Because Apollo taught us how to do the impossible. One of the most important lessons was the power of systems engineering. Before Apollo, most engineering projects were relatively straightforward. You had a problem, you designed a solution, you built it, you tested it, and you were done. But Apollo was different. Apollo was a system of systems, thousands of components that all had to work together perfectly. The Saturn V had to launch the spacecraft. The command module had to keep the crew alive. The Lunar Module had to land and take off. The guidance computers had to navigate. The communication systems had to work across vast distances. And all of these systems had to interface with each other, sharing data, coordinating operations, functioning as a unified whole. Managing this complexity required a new approach. NASA developed what they called systems engineering, a methodology for breaking down enormous problems into smaller, manageable pieces, then integrating those pieces back together. Every component was documented, every interface was defined, every requirement was traced from the top-level mission objectives down to individual parts. If a bolt failed, engineers could trace back through the documentation to understand why that bolt was there, what it was supposed to do, and what would happen if it broke. This level of rigor was unprecedented, and it became the template for every large-scale engineering project that followed. The International Space Station, the Space Shuttle, modern aircraft, even software development, they all use principles that were pioneered during Apollo. Another critical lesson was the importance of redundancy. In complex systems, things will fail. Components break. Software has bugs. Human operators make mistakes. You can't prevent all failures, but you can design systems that survive them. Apollo built redundancy into everything. The command module had multiple computers, multiple communication systems, multiple power sources. The parachute system could land safely with only 2 of 3 main chutes. The life support system had backup scrubbers, backup oxygen supplies, backup everything. Even the mission profiles included abort modes at every phase of flight. If something went wrong during launch, there were procedures to separate the command module and escape. If something went wrong during the moon landing, the astronauts could abort and return to orbit. NASA assumed that things would go wrong and designed accordingly. This philosophy saved lives. Apollo 12 was struck by lightning during launch, knocking out most of the spacecraft's electrical systems. But the backup systems kept working, and the crew was able to reset the main systems and continue the mission. Apollo 13 suffered a catastrophic explosion that destroyed half the service module. But the redundant systems in the Lunar Module kept the crew alive long enough to get home. Without redundancy, both missions would have ended in disaster. Testing was another cornerstone of Apollo's success. Everything was tested, and not just once. Components were tested individually, then tested as part of assemblies, then tested as part of complete systems. The Saturn V first stage was test-fired on the ground dozens of times before it ever flew. The F-1 engines were tested hundreds of times, including deliberate attempts to make them fail so engineers could understand their limits. The command module heat shield was tested in arc jets that simulated reentry heating. The spacesuits were tested in vacuum chambers, in swimming pools that simulated weightlessness, in thermal chambers that simulated the temperature extremes of space. The parachutes were tested by dropping test articles from aircraft at high altitude. Every system was pushed to its breaking point in testing so that engineers knew exactly how much margin they had. But testing had its limits. Some things couldn't be fully tested under real conditions. The heat shield couldn't be tested at lunar return velocities until it was actually used for lunar return. The ascent engine couldn't be tested in lunar gravity until it was fired on the moon. The Lunar Module landing gear couldn't be tested on actual lunar soil until it landed there. At some point, testing gave way to analysis, simulation, and calculated risk. The engineers did everything they could to reduce uncertainty, but they couldn't eliminate it entirely. Every Apollo mission was, in some sense, a test flight. The human element was crucial. Apollo was designed to be flown by humans, not just carried by them. The astronauts weren't passengers. They were pilots, and they had control authority over every critical system. If the computer failed, they could fly manually. If the automatic systems malfunctioned, they could override them. This human-in-the-loop design philosophy was controversial at the time. Some engineers argued that automation was more reliable than humans, that the astronauts were just adding weight and complexity. But the astronauts insisted on having control, and they were right. During Apollo 11's landing, when the computer was guiding them toward a boulder field, Armstrong took over and flew manually to a better site. During Apollo 12, when lightning knocked out the guidance platform, the crew was able to manually realign it using star sightings. During Apollo 13, when the automatic systems were failing, the crew manually configured the Lunar Module to serve as a lifeboat. Human judgment, human adaptability, human problem-solving under pressure, these were essential to Apollo's success. The machines were remarkable, but the people flying them were what made the missions work. Communication and collaboration were also vital. Apollo involved thousands of contractors, subcontractors, universities, and government agencies. Grumman built the Lunar Module. North American Aviation built the Command Module. Boeing built the Saturn V first stage. Douglas Aircraft built the third stage. IBM built the computers. MIT wrote the software. The list goes on. Coordinating all these organizations, ensuring they were all working toward the same goal, meeting the same standards, hitting the same schedules. That was a management challenge as difficult as the engineering itself. NASA established clear lines of communication, regular reviews, strict configuration management. They created a culture where problems were expected to be reported immediately, not hidden or downplayed. They encouraged engineers to speak up if they saw something wrong, regardless of their rank or position. This culture of openness and accountability was tested during Apollo 1. The fire that killed Grissom, White, and Chaffee was caused by a combination of design flaws, manufacturing defects, and procedural failures that had been identified by engineers but not addressed. After the fire, NASA completely overhauled their safety and quality assurance processes. They created independent safety panels with the authority to halt work if they found problems. They implemented formal hazard analyses for every system. They established flight readiness reviews where every anomaly, no matter how small, had to be resolved before launch. These changes were painful and expensive, but they worked. After Apollo 1, NASA flew 17 manned Apollo missions without losing another crew during flight. The cost of Apollo is often cited as an argument against ambitious space programs. The total cost was approximately $25 billion in 1960s money, which translates to about $280 billion in today's dollars when adjusted for inflation. That's an enormous sum, roughly 4% of the federal budget at the program's peak. Critics argue that the money could have been better spent on education, healthcare, infrastructure, or any number of other priorities. And they're not entirely wrong. Apollo was expensive, and the decision to pursue it was as much political as scientific. Kennedy wanted to beat the Soviets to demonstrate American technological superiority to win the space race. The scientific benefits, while real, were secondary to the geopolitical objectives. But the cost needs to be viewed in context. Apollo employed over 400,000 people directly and supported millions more in related industries. It drove advances in materials science, computer technology, telecommunications, and countless other fields. The integrated circuit, the microchip that powers modern electronics, might have been invented eventually, but Apollo's demand for lightweight, reliable computers accelerated its development by years or decades. The satellite technology used for GPS, weather forecasting, and global communications was built on the foundation of Apollo-era aerospace engineering. The medical devices that monitor heart rates and blood oxygen levels were derived from systems developed to monitor astronauts. The flame-retardant materials used in firefighter gear came from Apollo's spacesuit development. The list goes on. Calculating the return on investment for Apollo is difficult, but estimates suggest that for every dollar spent, the economy gained back $7 to $14 in new technologies, industries, and jobs. Perhaps the most profound impact of Apollo wasn't economic or technological, but cultural. For the first time in history, humans saw their planet from the outside. The photographs taken by Apollo astronauts, particularly the famous Earthrise image from Apollo 8, showing the blue Earth rising above the gray lunar horizon, fundamentally changed how we think about our place in the universe. That image helped launch the environmental movement, the realization that Earth is a fragile oasis in the vastness of space, that we're all sharing one small planet, and we need to take care of it. The overview effect, as astronauts call it, the cognitive shift that occurs when you see Earth from space and realize the interconnectedness of all life, has been described by nearly everyone who's experienced it. Apollo gave humanity that perspective. It let us see ourselves not as separate nations or tribes, but as one species on one world. Whether that perspective translated into meaningful action is debatable, but the awareness, the possibility, that came from Apollo. Apollo also demonstrated what humans can accomplish when we work together toward a common goal. In the 1960s, America was deeply divided. The Civil Rights Movement, the Vietnam War, political assassinations, social upheaval, it was a turbulent time. But Apollo was something that almost everyone could support. Democrats and Republicans, young and old, people of all races and backgrounds, they all watched the moon landing and felt pride. For a brief moment, we were united. That unity didn't last, of course. The Apollo program itself became a victim of its own success. After Apollo 11, public interest waned. People moved on to other concerns. The remaining moon missions received less and less attention, and by Apollo 17, the networks weren't even broadcasting the moonwalks in prime time. Budget cuts forced the cancellation of Apollo 18, 19, and 20. The Saturn V production line was shut down. The infrastructure that had been built to send humans to the moon was dismantled. We walked away from it, and we haven't been back since. Why did we stop? The reasons are complex. Partly, it was cost. Apollo was expensive, and once the political objective of beating the Soviets was achieved, there was less justification for continuing. Partly, it was risk. The more missions we flew, the more likely it became that we'd lose a crew, and the political cost of that seemed increasingly untenable. Partly, it was priorities. By the early 70s, America was facing economic problems, energy crises, social issues that seemed more pressing than lunar exploration. And partly, it was simply that we'd done it. We'd proven it was possible. We'd collected the rocks, taken the photographs, planted the flags. What more was there to do? This pragmatic view missed the point that many of the Apollo astronauts tried to make. The moon wasn't the destination. It was the beginning. Apollo was supposed to be the first step toward a sustained human presence in space, toward bases on the moon, missions to Mars, exploration of the solar system. But that vision required long-term commitment, long-term investment, and long-term thinking. And those are things that political systems struggle with. It's easier to fund a crash program with a clear deadline and objective than to fund an open-ended exploration program that might not produce results for decades. The engineering challenges of returning to the Moon today are, in some ways, easier than they were in the 1960s. We have better computers, better materials, better manufacturing techniques. We have decades of spaceflight experience to build on. We know more about the Moon, its environment, its resources, but in other ways, the challenges are harder. The industrial base that supported Apollo is gone. The engineers who designed the Saturn V are retired or dead. The institutional knowledge has been lost. The factories that built the spacecraft have been repurposed or demolished. We can't just dust off the old blueprints and build another Saturn V. We have to start over, designing new rockets, new spacecraft, new systems. And we have to do it in a political and economic environment that's very different from the 60s. There's no Cold War to drive urgency. There's no clear enemy to beat. The justification has to be scientific, economic, or inspirational, and those are harder sells than national security. NASA's current plan is to return humans to the Moon through the Artemis program, named after the Greek goddess who was Apollo's twin sister. Artemis aims to land the first woman and the first person of color on the Moon by the mid-2020s, establish a sustainable presence with a lunar gateway station in orbit, and eventually a base on the surface, and use the Moon as a proving ground for technologies needed for Mars missions. The Space Launch System, NASA's new heavy-lift rocket, is less powerful than the Saturn V, but uses more modern technology. The Orion spacecraft is larger and more capable than the Apollo command module. The lunar landers are being developed by commercial companies like SpaceX and Blue Origin, marking a shift toward public-private partnerships. Whether Artemis succeeds remains to be seen. The program has faced delays, cost overruns, and political challenges, but the goal is clear. Return to the Moon, this time to stay. The lessons of Apollo engineering are more relevant now than ever. As we contemplate missions to Mars, asteroid mining, space tourism, all the ambitious space projects of the 21st century, we're facing many of the same challenges that Apollo faced. How do you keep humans alive in the hostile environment of space for months or years? How do you build systems that are reliable enough to survive far from Earth with no possibility of rescue? How do you manage the complexity of missions that involve thousands of components and people? The answers Apollo developed: systems engineering, redundancy, rigorous testing, human-centered design, open communication. These principles still apply. But we also need to go beyond Apollo. The Apollo missions were short, days or weeks at most. Future missions will be longer, requiring closed-loop life support systems that can recycle air and water indefinitely. Apollo missions went to one destination, the Moon. Future missions might go to multiple destinations, requiring spacecraft that can be refueled and resupplied in space. Apollo was a government program funded by taxpayers. Future missions will likely involve commercial companies, international partnerships, new funding models. The engineering will be different, but the fundamental challenges remain the same. One of the criticisms of Apollo is that it was a stunt, a flags and footprints mission driven by politics rather than science. And there's truth to that. The scientific return from Apollo, while valuable, doesn't justify the cost if you're only looking at science. We brought back 842 pounds of moon rocks. We deployed some experiments. We took some measurements. But was that worth $25 billion? From a purely scientific standpoint, probably not. Robotic missions could have done much of the same science for a fraction of the cost. But that misses the larger point. Apollo wasn't just about science. It was about proving that humans could go to another world and return. It was about developing the technology and the knowledge to do it. It was about inspiration, showing what's possible when we commit ourselves to a goal. The value of Apollo can't be measured purely in moon rocks or scientific papers. It has to be measured in what it taught us, what it enabled, what it inspired. The astronauts who flew to the moon often talk about how the experience changed them. They describe the overview effect, seeing Earth from a distance and realizing how small and fragile it is. They talk about the stark contrast between the living Earth, with its blue oceans and white clouds and green continents, and the dead moon, gray and barren and lifeless. They talk about seeing the Earth as a whole, with no visible borders, no countries, just one planet. Frank Borman of Apollo 8 said that when he looked at Earth from lunar orbit, he realized that we're all riding through space together on this one small world, and we need to take care of it and each other. Jim Lovell, who flew to the moon twice, said that from space, Earth looks like a grand oasis in the vastness of space. Edgar Mitchell of Apollo 14 described a profound sense of connection, a realization that everything is interconnected, that we're all part of one living system. These aren't just poetic sentiments. They're observations from people who have a perspective that very few humans have ever had. And that perspective matters. It informs how we think about environmental issues, about international cooperation, about our responsibility to future generations. Apollo also demonstrated the power of setting ambitious goals. Kennedy's challenge to land on the moon before the end of the decade was audacious, arguably reckless. NASA didn't know if it was possible. The technology didn't exist. The risks were enormous. But Kennedy set the goal anyway, and it galvanized the nation. It gave hundreds of thousands of people something to work toward, a clear objective that was difficult but achievable with enough effort. And we did it. We achieved the goal with 5 months to spare. That success showed that ambitious goals, even ones that seem impossible, can be achieved if we commit to them. This lesson applies beyond space exploration. Climate change, poverty, disease, these are enormous challenges, but they're not insurmountable. If we can land humans on the moon, we can solve these problems too. It's a matter of commitment, resources, and willpower. But Apollo also showed the limits of short-term thinking. We went to the moon, achieved the goal, and then walked away. We built the infrastructure to support lunar missions, then dismantled it. We developed the expertise to design and build enormous rockets, then let that expertise fade as the engineers retired. We proved that humans could explore other worlds, then stopped exploring. This start-stop approach is expensive and inefficient. Every time we cancel a program and then restart it years later, we lose momentum, lose knowledge, and waste money redeveloping capabilities we once had. If we're serious about space exploration, about returning to the moon and going to Mars and beyond, we need sustained commitment. Not just for a few years, but for decades. We need programs that survive changes in political administrations, that have broad bipartisan support, that are seen as long-term investments in humanity's future rather than short-term political projects. The engineering of Apollo 11 was insane, but it was also methodical, rigorous, and ultimately successful. Every challenge was broken down into manageable problems. Every problem was solved through a combination of analysis, testing, and iteration. every solution was integrated into the larger system. The result was a series of machines that worked together to accomplish something that had never been done before. The Saturn V lifted the spacecraft off Earth. The command module kept the crew alive during the journey. The Lunar Module landed them on the Moon and brought them back. The guidance computers navigated across 250,000 miles of space with incredible precision. The communication systems kept them in contact with Earth. The spacesuits protected them on the lunar surface. The heat shield brought them home through the fire of reentry. Every system performed as designed, or close enough that the margins and redundancies covered the differences. And when problems did occur, the 12:02 alarms during the landing, the lightning strike on Apollo 12, the explosion on Apollo 13, the systems and the people responded, adapted, and overcame. The legacy of Apollo is complex. On one hand, it's a monument to human achievement, proof that we can do extraordinary things when we set our minds to it. On the other hand, it's a reminder of what we've lost, the capabilities we once had and let atrophy. We live in a world shaped by Apollo. The technology we use every day, the satellites that provide GPS and communications, the computers that fit in our pockets, the global interconnected culture, all of it traces back in part to the push to reach the Moon. But we also live in a world that has, in many ways, become smaller and more cautious. We've retreated from the audacious goals of the space age. We've become more focused on incremental improvements and less willing to take big risks. There are good reasons for this. Space exploration is expensive and dangerous, and we have many pressing problems here on Earth. But there's also something lost when we stop dreaming big, when we stop pushing the boundaries of what's possible. Apollo 11 happened more than 50 years ago. The astronauts who walked on the Moon are now in their 80s and 90s. Soon, there will be no one left who was there, who experienced it firsthand. The Moon landings will pass from living memory into history, joining the great explorations and achievements of the past. But the engineering, the knowledge, the lessons, those remain. They're encoded in the documents and designs, in the systems and methodologies that NASA developed, in the technologies that spun off into commercial applications. They're also encoded in the inspiration that Apollo provided to generations of engineers, scientists, and explorers who looked up at the Moon and thought, if we can go there, what else can we do? That inspiration is Apollo's most enduring legacy. Not the moon rocks or the flags or the footprints, but the idea that the impossible is just the difficult that hasn't been done yet. That with enough ingenuity, enough determination, enough willingness to take risks and learn from failures, humans can accomplish extraordinary things. Apollo 11 proved that. The insane engineering that made it possible, the Saturn V's raw power, the command module's sophisticated life support, the Lunar Module's alien functionality, the guidance computer's revolutionary software, all of it working together in a symphony of technology and human skill. It was insane, it was brilliant, and it worked.